Okay? So the process of solvation is different for different kinds of solutes and solvents. So what we're going to look at first is this kind of solvation, where we're dissolving ionic solutes in polar solvents. Okay? Remember, solutes are the thing that gets dissolved. Solvents are the thing that does the dissolving. In this reaction up here, what is the solute?
NaCl.
Yeah, it gets dissolved. And what's the solvent?
The Na plus
Water.
Oh.
The NaCl becoming that's the dissolving process. So this is the solute. This is the solvent. Water's doing the dissolving. Okay? This is being dissolved. That's doing the dissolving. So that's the solute. That's the solvent. Okay? All right. So let's try to remember. We talked about the structure of crystals of ionic things, and we looked at crystals of table salt under a microviewer. And what do they look like when we put them under the microviewer? Anybody remember what they look like? We looked at them, huh? Like a cube. They start out, what we have, the way we make that cube, at least the theory is, and I think the theory is pretty strong, is we have these alternating ions. Okay, it's not just one sodium and one chloride ion. They're chloride and sodium ions that are alternating in this crystal structure. Now I'm simplifying it. It's actually a little more complex than this, but we're simplifying it here. Okay, and I've done it sort of two-dimensionally here. But remember, it continues three-dimensionally. Going back away from what we're looking at here on this flat paper. Okay, so that it ends up, when you make it big enough, you can no longer see the individual ions. What you just see is that cube that you looked at under the microviewers. Okay? So in our last unit, we were talking about particle interactions. We never really got to particle interactions where ions and water molecules, which are polar, how they interact. We're going to deal with that now. Okay. So you should know the structure of water. We had a unit where we've actually built molecules and looked at how they can be polar and nonpolar and how you figure that out. And when we did that, we found that we've got oxygen bonded to hydrogen in a bent molecular structure. And when we did the electronegativity calculations, we found this was a polar molecule where the oxygen end is partially negative and the hydrogen ends are partially positive. And in fact, there's really two negative locations here because of the lone pairs that are sitting up there. We don't talk about much in this class. But the actual structure of a water molecule that would have a large oxygen atom and two hydrogen atoms that are sharing electrons here, and these are the partially positive and partially negative ends. Okay? So the oxygen has the partially negative end because it's far more electronegative than the hydrogen is. Okay? Alright, so those partially negative ends are attracted to these positive ions. Positives and negatives are attracted to each other. These partially positive ends down here are attracted to the negative ions because negatives and positives are attracted to each other. Okay? So let's look at this crystal over here. Just look at kind of one end of the crystal. Say this is one end of the crystal, and we just happen to have a sodium ion on that corner. And you have chlorine, sodium, and so forth stretching back in this crystal. Yes?
What's the difference between like tap water and distilled water?
Tap water has a lot of dissolved solids in them, and distilled water has far fewer. You take out most of the dissolved ions, you take out most of the dissolved particles that water treatment doesn't take out, like might gross some of you out, but little bitty things you can't, so small you can't see them, critters, you know, they're dead because they've been treated with chlorine. Yes? Yes. Okay. All right. So on this corner then, the negative end of the water molecules are going to be attracted to the sodium. Now I can only draw this in 2 dimensions, okay? So what we're going to do is draw the little water molecules kind of like this. Remember, that's that larger circle there represents the negative oxygen end of the water. And so they're just going to kind of group up along here, okay? Because they're attracted to that thing. All right? Now again, I can only draw this in 2 dimensions. Remember, this is going all the way around it as far as it can reach until it runs into a chlorine where it can't go there, you know, because of that negative end sort of pushes it away. But the chlorine molecule, the chlorine end, if I had a chlorine down here, well, let's make it a little larger, make a chlorine. Then the positive end, the hydrogen end of the waters are joined up to that chlorine. Oh yeah, sure. Okay, they're all grouping around the chlorine on that corner. All right, and here's something else you need to remember. We've talked about this in this class too. We often talk about solids being, you know, not moving around, but in fact, they're moving. Remember, all particles that are above absolute zero in temperature are moving. That's the nature of temperature. Temperature is the result of motion. So unless we're not at absolute zero, okay, we're way above that, 290 something degrees K above absolute zero, or not degrees, but 290 something K above absolute zero. And so these ions, even though they're fixed in place relatively to each other, they're twisting and turning, they're wiggling. Okay, constant movement there. The water molecules are constantly moving. And eventually, some of these sodium ions are moving fast enough, and the water molecules are sort of taking care of all of its need for, or most of its need for that negative charge. The reason it's attracted to the chlorine is because of the negative charge on the chlorine. So the negative positive, the partially negative waters supply all the negative that positive ion needs, and it lets go. It leaves the structure of the crystal. And when it leaves the structure of the crystal, the sodium ion that's now in the water is completely surrounded by water molecules. And they form a kind of skin or shell around the sodium ion. Okay? Now, I'm only drawing it in 2 dimensions. Remember, it covers the whole thing. It's surrounding the whole sodium ion. I'm making the sodium ion much bigger than it actually is relative to the water molecules, just to kind of show what's going on. Okay? All right, this whole process, the process where the water molecules join up to a sodium ion while it's on the crystal, the process of supplying that sodium ion with a negative partial charge the sodium needs, and the process of the sodium ion leaving and being completely surrounded, all of that together is the solvation process and describes the solvation of a sodium ion. Okay? The same thing happens with the chlorine, only it's the hydrogen end of the water, the partially positive ends of the water that are pushed up against where the chlorine is. And so when the chlorine ion, for the same reason, it's moving, it's wiggling, it leaves eventually, or some of them leave eventually, and you get the water molecules with the hydrogens, ends of the water anyway, joined up next to the chlorine. So remember, the small circle I've got here is the hydrogen end. Okay, and it completely surrounds it, encasing it, providing a kind of a skin or a shell around that of water molecules. And this is the solvation process for a chlorine ion, and together it's the solvation process for an ionic substance. So that's called solvation. It's called solvation. That process is called solvation. The specific kind of solvation here It's the solvation of an ionic solute in a polar solvent, water being the polar solvent. Okay? Now I have a question for you. If I were to give a quiz where I asked you to write a short essay where you described in detail the solvation process for an ionic solute and a polar solvent, could you do it? All right. So now's your chance to ask me any questions you need to be able to do that. So you understand well enough to be able to write that. Because that's the kind of stuff you need to know every day in this class. You need to be thinking, can I pass a quiz on this now? Because if you pass the quiz now, and you continue to study and review and things like that, you should be able to do fairly well on a test when it comes up. Okay? Huh? Describe the process of solvation of an ionic solute in a polar solvent. So all of this has to do with that process. I'm using illustrations and my words, what I'm saying, to describe the process. Can you do it?
So, is it just when the particles go from one to another?
Well, yeah, when they start out as a solid. So this is a tiny little piece of a much bigger crystal, right? And what I did was to describe why it is that the water molecules do what they do. The water molecules having these partially positive and negative ends in this sort of arrangement, they are attracted to the completely positive or completely negative particles that make up a sodium chloride crystal. And if they're kind of out on a corner, enough that I can get a lot of water molecules around there, and they wiggle enough, they're going to come loose, and because this water molecules take care of all their need for that opposite charge.
What conditions does it have to be before it becomes?
Well, it can't be a sodium that's like in the middle, because the water can't get to it. Does that make sense?
Yeah.
So you have to have it out on a corner somewhere. So the corners are where you can get more water molecules around it. And so the more water molecules you can get around it that are having this kind of polar to ionic attraction, the more you're able to satisfy that ion's need for that negative charge. And so when the wiggling gets just right, it makes it easier for it to break loose. Yeah.
Well, like as it breaks, if you thought this is how it starts working on the next group.
Sure. Anytime you break one off, you provide a new corner, don't you? Okay, yeah.
And it has to be in crystal form for it to. Does it have to be
No, I mean, no, ionic substances just naturally form crystals when they're solids. Okay? They don't have to be, they just are. Yeah.
You see where you got the Na plus and like circle?
Yeah, this?
Yeah, the big circle around there is oxygen, right?
Yeah, the big circle is the oxygen. Remember, the oxygen is bigger than hydrogen, obviously, right? Oxygen has, 15 or 16 protons and 16 electrons, where hydrogen just has one of each.
And it's a negative in here, so
Yeah.
it'll be on the plus.
Yeah, the water end, since it's negative, tends to get up next to the positively charged sodium ion. It's attracted to it.
And then the hydrogen is attracted to the chlorine.
Yeah.
The positive.
Right. Right. I mean, you've probably seen dust collect on something that has a static charge, right? Kind of works the same way. Those opposite charges are attracting.
So what are those little particles that you have like thrown in there?
Here?
Negative? Yeah.
Here?
It's
Yeah.
hydrogen. I mean,
These are water molecules. They're just really smaller versions of this drawing right here.
So when the conditions are right or whatever, like on the outer circles, they'll break loose and they go to the positive.
Exactly. So the positive end of the water is attracted to the negative end of the negative ion. And the negative end of water is attracted to the positive ion. And all they have to do is spin around.
So basically, you're just saying the ionic equation turns into the positive commit with the negative and it's positive.
So you're talking about this, when I see they say the equation, you're talking about this equation?
Like you said, to describe it. So basically, just the positive little ion commit with the negative ion and it's positive.
Yeah, but these aren't ions. These are polar. They're molecules that have a polar ends. They're dipoles. But they do connect. But they're connected just by opposite charges. They're kind of like magnets are attracted. Okay, they're not really part of the same thing. They just have a force that's attracting them because of the opposite charges.
That's what I'm saying.
Okay.
When you say it, would that be like not describing it good enough, or is it?
Well, if you're describing the solvation process, you have to describe the whole process. Okay? You have sodium and chloride crystals forming this structure, making a crystal. You have oppositely charged ends on a water. They're attracted to the structure here at the corners, providing the need for this sodium positive charge, its need for that negative charge, and the water has that partially negative charge, so I put a bunch of them around there. Takes care of it. Wiggling, it leaves, it completely surrounded. That's the whole solvation process.
So it basically just depends on the element that got what kind of charge, and then tell what kind of charge it needs.
Yeah. Yeah. I mean, you're basically telling a story. You know, if you were to write a story, you could tell how, you know, little Timmy, you know, went down the street and he did all the, you know, whatever, okay? Okay, fine. Whatever kind of story you want to tell. But the point is, you could fill in the details, couldn't you, for what happened to little Timmy and why, right? Well, you can do that. That's what I'm asking you to do here. Can you fill in the details of why the little water molecules did what they did? Okay, why did this little Timmy, you know, and all the other little Timmys break off that sodium ion?
Those are ionic solutes. Like
Yeah, since sodium chloride is being dissolved, it's the solute. And water is doing the dissolving. It's grabbing hold here and eventually pulling it loose. It's the solvent, right? And all together, this whole storyline describes the solvation process. Okay? That makes sense? See, those are really, really good questions. So you guys are asking questions. Pat yourself on the back. Y'all did a really good job. That's taking charge of your own learning. That's saying, I want to understand so I can do well. So I can actually use this stuff. You only can use the stuff you understand. All right? I mean, some things you do until you understand it. That happens too. That's part of the learning process. Some things you understand in order to use it. And all together, it all works together eventually. Because once you learn to do and understand one thing, you build on that to learn and do something else. And you get more and more complex. Okay? And that's what you have to do. That makes sense? All right, that's one kind of solvation process.